This video will cover the idea of capture-recapture. You should by the end be able to understand what it is, the concept behind how it works, and when you should use the formula as appropriate in exam questions. This question is for you viewers to first have a think about. We have a lake, and for the purpose of this video, we are going to assume that they are the same species. If you were to do this, how would you calculate an estimate for the number of fish in the lake? When I first learned this, I was asked the same question. If you do GCSE biology, you may have come across finding an estimate of the population for daisies or something similar. So I applied this to the context provided here. Let's say I split the lake into 16 equal chunks, like this, and then I decide to sample 3 random parts. I'll then take the average and then multiply by the 16 chunks I made to get the population. But unfortunately, this doesn't work. The reason for this is as follows. Here is a fish. Let's call it Greg. Now, I sample section 1 on the grid, and Greg is there. All is well, he is included in my sample. Now, let's say I move along the lake to section 2 in order to collect that sample. But hang on a minute, Greg is moving to that section. And I don't know how to differentiate between different fish, so I would probably unknowingly include him in the second sample. He might even decide that he wants to be part of the third sample. Couple this with a few hundred or 1,000 fish doing the same thing, and we have a problem of an overestimate because so many fish are included in multiple samples. It works the other way too. If the fish decides to move away just before I could catch them, then the sample count for sections 1, 2, and 3 will be too low. So we could say that a moving population gives biased results. As I earlier stated, what we'll find is that with so many fish, we cannot count the population in its entirety because it would take far too long. You might be feeling stumped at this point. If so, there is a way around this, and we'll take a look at this now. Now, there are many ways to not only explain the concept, but also to go about solving, if that's what you want to call it. What we are solving for we will come to in a bit. Some may use proportions, while others might use some form of algebra. I would always use the latter as an equation, and it can be demonstrated by uppercase m over uppercase n, which equals lowercase m over lowercase n. This makes no sense on its own. What does each letter mean? Let's start with capital N. This is the size of the population to be estimated, commonly what exam questions ask you to find. The next letter, capital M, represents the number of individuals that you initially sample. When we sample, what we do is tag them, whatever you're trying to sample, which will help later on. Now for lowercase n. This is just the number of individuals in your second sample. Lowercase m has a bit more to it. Remember the tags earlier? Well, this letter represents how many of your second sample here have a tag. I am going to point out, if you are mathematically comfortable, you could be inclined to simplify the equation. I've done the rearranging for you, so you just have to memorize it. I should warn you though, you will not always be asked to find the population, the capital N. It could also be the number originally tagged or something else, etc., etc. Again, only if you are comfortable with rearranging, go ahead. Don't take the risk thinking that this is a shortcut. As always, everything becomes, at the very least, a little easier when explained with an example. Let's go back to the lake earlier. I'll randomly sample some fish at this location here. Then I'll tag them. I decide to sample and tag 50 fish at the start, so this means that uppercase M is 50. A week later, I return to the same spot and take yet another sample. This time, we just observe. It's likely some fish will have tags and some will not. My second sample consists of 30 fish, and of those, 5 are tagged. So lowercase m is 5 and lowercase n would be 30. I've put the formula here for reference. Now we have the values and it's become clear what we are trying to solve. N, or in other words, for population. It's self-explanatory. Stick the numbers in and you'll end up with this. 50 over n equals 5 over 30. To get one side in terms of n, we'll multiply both sides by n. This leaves us with 5, which equals 5n over 30. Remove the denominator of 30, and remember, since the denominator divides, we need to multiply. This means that 5n is equal to 1,500, and in order to isolate n on its own, you can divide by 5 to get a final answer of 300. The next thing we'll do is summarize the process of the Recapture method. This is particularly useful if you need to copy some notes down. To summarize, we need to firstly take a sample and then mark them. You can then release the fish or the sample back into the population, and the point I should have mentioned earlier, make sure that they mix in thoroughly with the population. This is key to the method's integrity. You then wait some time before taking your second sample. Remember, it needs to be in the same location. Then, you'll need to count the number of tags you see in the second sample. Use these figures to estimate whatever you need using the formula earlier in the video. And remember, it's exactly that, an estimate. Some more writing and explanations now. Sorry about that. We need to look at the assumptions of the Recapture method. This is another one of those things that is typically asked in exam questions. It isn't hard at all, you just need to be able to understand and just remember some of these points. The first thing that we assume is that it is a closed population. This means that there were no, in theory, births, deaths, or any migration between the time of the samples. The second is that the probability of capture is equal for all members of the population. This can be achieved by a random sample. Thirdly, we assume that the sample has no effect on the individual's chance of survival and that the tags have not come off. There must be time for the population to mix, and this is assumed. And finally, the sample is large enough to be representative. In other words, it needs to be large enough to mean something. Now, that is a lot to memorize, so I have highlighted the key ones that I think are easiest to remember and are found in the mark schemes. This is the part of the video where I go through some exam questions. If you are feeling confident, why not have a go, and if you get these right, check out the video's description for free exam worksheets on this topic. A researcher wants to estimate the number of ducks in the park. In the first sample, she catches and tags 60 ducks. A few days later, she captures a second sample of 40 ducks. 12 of these are tagged. Estimate the number of ducks in the park. So again, I'll highlight the key pieces of information which will plug into our equation. Since her first sample was size 60, we can say uppercase M is 60. This will be over what we are trying to find, the population, or n. This will equal the number tagged, which is either 12 or the lowercase m, and this will be over 40. If we multiply by n to eliminate it, we get 60 equals 12n over 40. Then multiplying by 40 leaves us with 12n, which equals 2,400. In order to get n on its own, we need to divide by 12. And doing so gives us an estimate of the population as 200 ducks. Now, you may have noticed these letters in blue here. These are for the examiners when they mark your answers. B1, as it is called, is essentially a process mark, or your workings. You can get it for any of these stages, even the rocket on a specific line. A1 is an accuracy mark. It is important you make your answer very clear to the examiner so they can award it. Don't use a highlighter though to underline your answer, because all they'll see is the highlighter and not your answer. This is for all the exams you sit, by the way. Now for the next question, Liam wants to estimate the number of pigeons in the park. He catches a sample of 60 pigeons in the park, tags each of them, and then releases them. A week later, he catches a sample of 25 pigeons in the park and uses the Peterson Recapture formula to estimate that there are 300 pigeons in the park. Work out how many of the 25 pigeons in the sample had a tab. This question has 2 marks available, as have been all of these relatively easy questions so far. You need to get good at doing these to maximize your marks. Try and have a go with this one, as this is a real application rather than just following a method. Highlighting the key information, I'll display the formula for this one along with the values given. We get uppercase M as 60, uppercase N as 300, and lowercase n as 25. I have put it back here for you to see again. The hardest bit has actually been done. Again, we are just plugging numbers in at this point. So 60 over 300 equals something over 25. I'll rearrange for m, and by doing so, I'll multiply this 25 here, as again, the denominator is currently dividing, and this gives m, which was the number tagged in the second sample, as 5. Part B of this question asks us to comment on the reliability of Liam's estimate and considering his assumptions. Now, you can go back for yourself and read the question. It said, a week later. This is a key component to the assumption part. We can just use the 2 assumptions earlier in the video since they are fine for this question. However, it is the third mark that comes from stating if it is reliable or not. In our case, since it was a week and pigeons could fly, it probably wouldn't be reliable since they could migrate. Here are some more valid but unlikely points to add in red. As always, thank you for watching this video. There will be worksheets in the video's description for you to have a go. If you did find it useful, please like and subscribe, and I'll answer any questions in the comment section below. And in the lead up to mocks and exams, please share this with someone who will benefit.